So, good morning, everybody. First of all, I hope that everyone is okay. So, we are going to start these presentations to support the materials that is already published in Phoenix. So, this is a theoretical lecture in which we are going to speak about special cases that we may have to deal with related with linear programming. Um, in this presentation, we will see three cases. We will look to the degenerated solution. We will also look to multiple optimal solutions and also to unlimited solutions. So let's start with the degenerated solution. So, as usual, I like to speak about these subjects with examples. So here on the left, you have the problem that we are going to work with, and here on the right, we have the transformation of these expressions so that we can build the simplex table. So as you know, in the line of Z, we put everything in the first hand side, and in the restrictions, we introduce the slack variables. So we have here two slack variables, S1 and S2, because we have two restrictions. So to build the initial simplex table, we just consider a line for each of these expressions. So one line for Z, one line for the first restriction, and another line for the second restriction. We start listing by first the decision variables x1 and x2, and then we consider the slack variables s1 and s2 and independent term. And then we just fill here in the table the coefficients. For example, -3 and -4 in the case of Z. In the end, we have 0. And 1 and 2 for the first restriction in x1 and x2. Then 1 in s1 and 9 here in independent term, and so on. So, although the objective is to speak about the degenerated solution, in this example, I'm going to explain in detail how the simplex method works. So, in this way, this is a way of we revise the simplex method. Okay. So, in the other two cases, I will present on the essential aspects, but now the objective is to go through in detail through the simplex method. So what we need to do first is to identify in this table, in the initial table, the basic and non-basic variables. So I choose as basic this one, S1 and S2, because I can identify this unit vector here. Okay, so 1 here and 0 in the other two places. The same here. The S2 is a unit vector. And I identify here this as a basic variable, and S1 S2 we say that they are the base. Okay, so this means that the other two variables are considered non-basic. So the purpose of doing this classification is because in this way we are able to extract a solution. For example, if we consider x1 and x2 0 in these expressions, we can extract immediately that s1 is 9, s2 is 18, and z is 0. Okay, and in this way we are also able to say that this solution is not optimal. Okay, so here we try to explain why the solution is not optimal. So the solution that we extracted from these expressions or from the previous table is if we consider x1 and x2 as 0, that is the non-basic variables, we then obtain directly z equals 0, s1 is 9, s2 is 18. However, we also have the partial derivative of z in order to x2 as 4. That is, it's a greater it's a positive quantity. So the combination of these results, that is this partial derivative in relation to a variable that we are assigning the value 0, tell us that this solution is not optimal. Because it's not optimal because if we change this condition, and we can change it because it can only be positive, we can change it only increasing x2. But if we increase x2, then from here we conclude that z can also increase. That is, we can improve the solution. So this solution is not optimal. Okay. So what we need to do next is to change this classification. Okay. So these are not the variables that we can set equal to 0. Okay. So, and to do this, we identify that this one, x2, now should go to the base, okay? And one of these, S1 and or S2, one of these must leave. To check which of these should go out, what we do here is that we evaluate the values that x2 will have in the next iteration when it enters to the base. So, and to do that, we just divide these coefficients here by these coefficients here. So 9 divided by 1 is 9, and 18 divided by 3 is 6. So we need to extract S2. Otherwise, we will have negative values. And as we can see here, the problem cannot have negative values. So the only possibility is to extract x2. Now, we need to transform this table so that here, this column will be replaced by a unit vector, as this one, okay? So here we identify the operations that we need to perform so that we transform x2 in a basic variable. So this element here identifies what we call the pivot. And our objective is to first transform this element in 1. And to do this, we write this instruction. So what I'm saying here is that I have here this is the 3 line of the table. So I need to consider the previous line, that is the line of the previous table, and we need to divide it. So we need to divide all elements by 3. This is what is done here. So line 3, the new line 3, is the previous one divided by 3. So 2 divided by 3, 3 divided by 3, it's 1. Here you have 0. Here you have 1 divided by 3, and here you have 6. Okay? So next, what we need to do is to transform these two coefficients in 0. So let's start first with the line of z, which is identified here as L1. Okay, so this symbol just means that it's the previous L1. So our objective is to put a 0 here. So, and to do that, what I'm going to do is that I'm going to start with the previous line, and I'm going to use this one, the new line 3, and I'm going to multiply it by a coefficient, in this case 4, which is the symmetric of this. Okay, so, and this instruction, to implement this instruction, I use this table here. So I start with the previous line 1, then I multiply line 3, this line 1, this line here, okay, by 4, and I put it here, okay, and then I just need to add the coefficients, and when I do that, I get the new line 1, okay. So what I'm going to do next is to do the same, but now for the second line. So this is the previous table. We have here the second line, and we also have here the line 3. So the new line 2 is the previous line 2. In this case, I just need to subtract line 3 because coefficient here is 1. Okay, so and again, this instruction is implemented here. We start with the previous line 2, then we get line 3 multiplied by -1 in this line, and finally we get, when we add these coefficients, we add the coefficients of the new line 2. So here we have what we have done. So first for line 1, then for line 2, and then for line 3. So we just need to build a new table with these 3 new lines. Okay. Then what we do is that we identify the new basic variable. This one remains basic, and we identify here the new basic variables also. Okay. Well, again, we look to this table. We can extract a solution. Okay. The solution, of course, is obtained considering these 2 variables, x1 and x2, as non-basic. So that is, we will assign 0 to them, and then we extract the value of these 3, z 24, s1 3, x2 6. However, since we have this negative here, negative coefficient here, in relation to a variable that we will assign the value 0, so we conclude that the solution is not optimal. Remember that negative values here, they mean positive partial derivatives. So z will increase if we increase x1. So it's not optimal. Again, this variable should enter in the base, and one of these should leave the base. To check which of these should leave the base, we repeat the process. So we evaluate first the values that x1 will have in the next iteration. But when we do this now, what we see is that we have 2 possibilities. So both s1 or x2 can go out. So what we are going to do is that we will extract first s1, and then we will check what happens if we extract x2. Okay, so if we decide to extract s1, so what we have here now, this is the new pivot element. The objective is first is to put this coefficient equal to 1. So we just need to get this line and divide it by 3. Multiply it by 3, which is divided by 1/3. And then we need to put 0 here and 0 here. And the instructions to do this, they are represented here. So I'm not going to do it in detail. I'm just going to present you the next table. So, and here we have our table. So this table, we have here the basic vectors, okay, x1 and x2. The column of x1, the column of x2. So these ones are non-basic. So this means that we are going to assign 0 to s1 and 0 to s2 to extract the value of z, which is 27, the value of x1, which is 9, and now the value of x2, which is 0. So what's the problem? So we have only one variable different from 0. We have 2 restrictions, but only one variable different from 0. Okay. So let's see what's happened if we decide to. If we decide to extract x2 instead of s1. So if we decide to extract x2, so we will have this new table, and the basic variables now are x1 and s1. This means that we are going to consider x2 0 and s2 0, and if you do that, we extract z27, s1 0, and x1 9. So the classification of variables is different now, but the solution is the same. So only x1 is different from 0. So we need to understand why this happens. Why do we have less variables equal greater than 0 than the number of restrictions? And to understand this in detail, we need to look to the graphical solution of this problem. So this is what I'm going to show next. So to build the graphical solution, as you already know, we need first to identify the solution domain. So, and to identify the solution domain is something that we do working with the restriction. That is, we need to identify the boundary that each restriction defines. And to do that, we just evaluate the points in the axis in which the lines that define the restrictions cross. To identify the vertical point, we consider x1 equal to 0, and we extract, in this case, 9. To identify the horizontal point in which this line crosses, we consider x2 equals 0, and we get x1 equal to 9. So in the second restriction, we do the same. So considering first x1 equal to 0, we extract x2 equal to 6. Then consider x2 equal to 0, we extract x1 equal to 9. And we can do the same to the line of z. We saw that the optimal value of z was 27. So we can see what is the shape of the line z equal 27. So evaluating this function, this line. So we do the same. If we consider x1 equal to 0, we see that this line will cross the vertical axis in 675. If we consider x2 equal to 0, we see that this line will cross the axis in x1 equal to 9. So graphically, this is the result. So we have here in blue the line related with the first restriction, and in red the line related with the second restriction, and in pink we have the isoline of z equal 27. Okay, so and through this picture we can identify why we have degenerated solutions, at least in 2 dimensions. Okay, so we see that this is the optimal point, the point x1 equal to 9. So, and what we can see is that in this figure, so we are working in 2 dimensions, but we have here a point that belongs to the solution domain, the point x1 equal to 9, which is defined by 3 lines. So we have the horizontal axis, we have the 2, and we have the 2 restrictions. So we have 3 lines that define this point. But in 2 dimensions, we just need 2 lines to define a point. So we conclude that we have more information in our problem than necessary to define the solution domain. So we can see that this restriction number 1 is not contributing for the definition of the solution domain. Okay, so we have excess of information in our problem. The solution domain is just this region defined by the axis, the horizontal and the vertical, and the red line, the line corresponding to the second restriction. Okay, so to conclude, degenerated solutions, they arise when we include in the problem information that is not necessary. Okay, so let's look now to the optimal multiple solutions. Again, we are going to use this example. So we want to maximize the function z, which is defined by x1 and 2x2, and we consider these 2 restrictions. Okay. Now, our first step, so we are going to present both the the simplex solution and the graphical solution. The objective is to understand the behavior of the simplex method, but to to understand exactly what's happening, we will use also the graphical solution. Okay. So our first step is to transform these inequalities, introducing the slack variables S1 and S2, and then we build the initial table. Okay. So after building the initial table, we classify our variables as basic S1 and S2 and non-basic X1 and X2. So with this classification, as before, we get an initial solution, which is presented here. Okay, and we conclude also that solution is not optimal because we have this negative coefficient here. So if it is not optimal, we need to change it. If we are going to change it, we need to we want to x2 in the base. So to see which goes out, S1 or S2, we evaluate here the values that x2 can assume in the next iteration. So divide x1 6 by 1, we get 6, and then divide 10 by 2, we get 5. So we need to select S2 to go out to avoid the negative values of variables. So doing this, that is introducing x2 in the base, lead us to the second table. I'm sorry, table number 1. The previous one was table 0. If we analyze this table, we start to analyze this table. I'm sorry. We start first by classifying the variables as basic. So S1 and X2 are basic ones, and X1 and S2 are non-basic. So we list here S1 and X2. So we conclude that this table is optimal because there are no negative coefficients here. Okay. Nevertheless, we have a 0 here. 0, a coefficient of z equal to 0 in a variable that we intend to set equal to 0. So what we can conclude is that now, since the partial derivative is 0, we in fact can change this condition x1 equal to 0. We can increase it because since the partial derivative is 0, if we change x1, nothing will happen to z. So z will be maintained equal to 10. And to do this, we test what's happened if we decide to include x1 in the base. So including x1 in the base is simply transforming this column in a unit vector. So to do this, we just need to evaluate the values that x1 will assume in the next iteration. And we need to choose the lowest possibility. So S1 must leave the base. So this table gives us this solution. Okay, with x1, s2 equal to 0, we get z is 10, s1 is 1, and x2 is 5. But after this transformation, we get this table, which is also optimal. And as expected, we have the same value of z, but now we have a different solution. x1 is 2 and x2 is 4. Again, this is also an optimal table because there are no coefficients, negative coefficients here in the non-basic variables. We still have a 0 here. Okay, so we have these two solutions. And the two are valid solutions because they have the same value of z, and they don't violate the restrictions, so they are two valid solutions. So let's see graphically what happens. Before that, before looking to the graphical solution, so it's important to note that the simplex method just gives us basic solution. That is, basic solutions are the vertices of the solution domain. So what we are obtaining here and here is just two vertices. And what we can see here, so this is the graphical solution. We just need to represent the first restriction, the second restriction. This is the line in pink. We have the line z equal to 10. And these two points here, identified here by these arrows, are in fact the solutions that we obtained previously with the simplex method. In the first case, the first solution is this one, and second one is this one. So now, since we have here the line of z, we can conclude that all these points in this small segment of the second jurisdiction, all of them must also be solutions of our problem, because they belong to the solution domain, and the value of z in these points is also 10. So all of them are also solutions of our optimal solutions of our problem. Okay, so the simplex method just gives you the solutions in the vertice, but in fact all of them are solutions. Nevertheless, these solutions here, so in the middle of these 2 points, they are not basic solutions. We can see it clearly because, for example, a point here will have coordinates x1 and x2 different from 0. So, and also, since you are far from restriction number 1, s1 is also different from 0. So here in these points, we have 3 variables different from 0 and only one equal to 0. So these points are not basic solutions. Okay, and the last problem that we are going to analyze in this talk is related with unlimited solutions. So to illustrate, again, we use this example. We have also a two-dimensional problem because, again, we need to analyze this problem both using the simplex method and graphically to understand precisely what's happening. So starting with the initial table, we are able to extract an initial solution. So it's the one that is presented here. And we are able to conclude that the solution is not optimal because we have this negative coefficient. So x2 is going to the base and it will assume the value 2 or minus 3. We can use this one because no negative values are allowed. So as stated here. So s2 must go out. So this is the pivot, it is already 1, so we just need to transform these two coefficients here. And doing that, we arrive to this table, okay? So this is a valid solution, what we have here, because we can identify here the basic variables and the non-basic variables, okay? So setting these two, x1 and s1 equal to 0, will allow us to say that z is 10, S2 is 2, and S2 is 10. So it's a valid solution. But again, it's not optimal. It's not optimal because we have here this negative coefficient. So it must go to the base. To go to the base, we need to see which of these goes out. However, when we try to do that, so dividing 2 by minus 2 is minus 1, dividing 10 by minus 2 it's minus 3.3. So we cannot make x1 a basic variable because we cannot extract one of these. So we are blocked. We cannot proceed. So the simplex method just gives us this information. So when we have something like this in simplex method, so what's happening is that the solution is not limited, and we can conclude that analyzing what's happening graphically. So let's do that. So in this figure, what we represent, first we have here the restriction, the line representing restriction 1 in blue. In red, the line representing restriction 2, and the pink line here represents z equal to 4, which was the z of there is a mistake here in the table. Okay, so z is is 4, not 10. I will correct that. So this line is the line corresponding to the point that the simplex method was able to evaluate. It's this point here. So, but we can evaluate other lines of z. For example, line z equal to 6 presented here in orange. So in this way, comparing these two lines, we conclude that the lines of z grow in this direction. Okay, so but the solution domain has no limitations in this direction. So z will tend to infinite. So the solution is unlimited. And this is it. So this is our first lecture. So I think now you should go through the materials that I provided in Phoenix, and I will try to schedule a talk for for the clarification of any doubts that you can have related with this material. So that's it for this lecture. Bye. See you soon.